Hello. In this lesson, we'll look at how to realize a common source amplifier with as high a gain as possible. Okay. As an example, let's take a PMOS common source amplifier. Now, this is what a PMOS common source amplifier looks like. I have not shown any of the biasing arrangements to keep things simple. I'll assume that the gate is biased at some voltage VGP and an incremental input Vi is applied to that. So this means that at the bias point or the operating point, we have the source gate voltage of the PMOS transistor to be VDD minus VGP. Okay, and a certain current ID flows through the PMOS transistor given by the square law equation at the operating point, and it's given by mu p Cox by 2 W by L VSG minus VT square, and the output bias point, the output operating point would be the operating point current times RL. Okay, and we also know that when we apply an incremental signal Vi, there will be an incremental signal Vo, and we are already quite familiar with the common source amplifier. We know that the gain for the signal is minus GM RL. Okay. Now, how do we increase the gain? When I say increase the gain, how do we increase the gain magnitude? The magnitude of the gain is GM times RL, and we have to increase it. In order to do that, we have to either increase GM or increase RL. Okay, and how do we do either of these things? We can increase GM by increasing the bias current ID or increasing the aspect ratio W by L of the MOS transistor, or we can increase RL. Now, neither of these things comes for free. To see that clearly, let's look at this expression and relate it to the bias current. And we know that one of the ways to express GM is to write it as 2 times the current in the MOS transistor divided by the source gate voltage minus the threshold voltage. This is the gate overdrive voltage. Okay, so the gain magnitude turns out to be 2 times IDRL divided by VSG minus VT. Okay, now it's very easy to see that this ID times RL, that is nothing but the operating point voltage across the load resistor RL. Okay. Now this tells us, let me call this VR, it's the operating point voltage across the load resistor RL. So the gain magnitude GMRL is 2 times VRL divided by the overdrive voltage VSG minus VT. Okay. Now how do we increase the gain? We have to increase VRL or we have to decrease VSG minus VT. Now first let's look at decreasing VSG minus VT. Now this expression makes it look like the gain will monotonically increase as we decrease VSG minus VT, but it turns out that the square law model that we use is valid only if VSG minus VT is much greater than the thermal voltage kT by Q, where K is Boltzmann's constant, T is the absolute temperature, and Q is electron charge. And we know that this is about 25 millivolts at 300 Kelvin or 27 degrees Celsius. So this VSG minus VT has to be about 200 millivolts or more in order for the square law model to be valid. And what is the square law model? That is the model that says that the current in saturation region is mu Cox by 2 W by L VSG minus VT squared. Okay. Now we won't go into details of what happens if VSG minus VT falls below this. You can still operate it like a transistor, except that the current will not follow this expression. And it also turns out that as VSG minus VT falls below 200 millivolts or so, the gain does not follow this expression, which was of course derived from square law. And even if you decrease VSG minus VT below that, the gain does not increase. You start from large values of VSG minus VT, you go down to about 200 or 150 millivolts, the gain goes on increasing, but below that the gain will saturate to some value. So we have to keep a minimum VSG minus VT, and for our purposes we will say that it has to be greater than 200 millivolts for operation in saturation region. So clearly, by decreasing VSG minus VT, we can increase the gain to some extent, but not indefinitely. So the only way is to increase this DC or operating point drop across the resistor RL, VRL. Okay. Now that looks fine as well. What is the problem with that? We know that we have to maintain this transistor in saturation region for it to work like an amplifier. So across the drain source we need to have at least VSG minus VT at the operating point for it to remain in saturation region. And across the resistor we of course have VRL. Okay. So the supply voltage is a sum of the source drain voltage of the PMOS transistor and the voltage across the resistor. Okay. So VDD, which is the source drain voltage of the PMOS plus VRL. This is equal to greater than or equal to VSG minus VT of the MOS transistor plus the voltage drop across the resistor. And we already know that this itself has to be more than 200 millivolts for operation in saturation region. So basically we have to choose a supply voltage that is greater than the voltage drop that we want across the resistor plus 200 millivolts or so to keep the transistor in saturation region, to accommodate the transistor. Okay, so now we see that if we increase VRL, we have to increase VDD. Okay, so we have to use larger and larger supply voltages, and to get a feel for numbers, let's see the kind of numbers we are talking about. This expression is nice in that it directly relates the gain. It relates the gain directly to the DC voltage across RL at the operating point and the gate overdrive VSD minus VT of the MOS transistor. So if we want a gain of 10, we want 2 times VRL divided by VSD minus VT to be 10. Let's choose VSD minus VT to be 200 millivolts, which is, let's say, the minimum possible. So the numerator must be 2 volts in order to get a gain of 10. So VRL should be 1 volt. Now in this case, the total supply voltage has to be 1 volt plus 200 millivolts or 1.2 volts, which is quite small. Okay, this is for a gain of 10. Now let's try a gain of 100. The denominator is 200 millivolts. The gain is 100 equals 2 times the voltage across the resistor. In this case, the numerator has to be 20 volts or the voltage across the resistor has to be 10 volts. And the total supply voltage is greater than 10 volts plus 200 millivolts or 10.2 volts. This looks manageable, but you may have heard that with modern processes, supply voltage is reducing. So compared to modern standards, this is a high supply voltage. And if you try to increase the gain further, let's say into the thousands, the supply voltage will become hundreds of volts and it's really not manageable. And also please keep in mind that this is the minimum supply voltage that is required. We have not taken swing limits into account and so on, because if we do make an amplifier of a large gain, we do expect a large swing at the output, and we cannot set the operating point such that the MOS transistor is at the edge of saturation region. It has to be biased far away from that, so that along with the signal swing it comes to saturation region. So let's say we are limited to a modest supply voltage of about 5 volts. Then we can see that the gain that we can get is not more than 10 or 20. It's harder to get gains more than that. Okay, so we have to devise some other technique for realizing large gains, which we do need. Okay, you know that an op-amp, for instance, which is one of the ubiquitous building blocks of analog design, has a very large gain, probably up to 1 million, and we have to see how we can realize such a large gain. Okay, we'll see how to do that in the following lessons.